Good morning, everybody. So we're going to pick back up. Probably need about half the lecture here to finish Chapter 7 before we get into some review for next week's midterm. I wanted to start back with the slide that we were on last time. We were talking about the increasing ionization energy. So let's talk about generally why ionization energy increases from left to right. So let's look at this trend first. And so we can be thinking about the energy of electrostatic, either repulsion or attraction, how this is equal to kappa Q1 Q2 divided by the distance of separation. And so we're thinking here the nuclear charge, or maybe better, the effective nuclear charge that makes its way out to the outer valence electrons. So imagine you're a valence electron for, say, sodium in a 3s. Relatively small effective charge compared to something like chlorine on this side of the periodic table. So if you're comparing sodium to chlorine, you see chlorine's ionization energy is a lot higher, because chlorine's now going to be smaller due to the increased charge. So we got two things going on. We have the effective nuclear charge increasing from left to right. So from left to right, our effective charge is going up, and then also our size is decreasing. So the effective charge is having the effect from sodium to magnesium to aluminum. We're decreasing in size. Now the only peculiar trend to explain is why we get this increase and then a slight decrease, and then back to increase, and a little bit of a decrease, and then back to an increase. Why do we have this periodic inconsistency with the boron group of elements being a little bit lower than the preceding element in ionization energy, and the same thing with the oxygen group? Well, we have two things going on. First thing, we're thinking sodium's ionization from a 3s. So if we're thinking sodium to magnesium in terms of relative size, this is probably showing it to too big of an extent. But magnesium is smaller. Aluminum, if we're thinking of the 3s orbital, the 3s orbital would be smaller, but then you have this 3p orbital. So the 3p orbital is just a bigger orbital. And so now we're removing an electron from aluminum from a 3p orbital, not from that 3s orbital. So the 3s orbitals are all shrinking in size as we're going from left to right because the atoms are going smaller, but that 3p orbital just happens on average to be a little bit bigger than the 3s. So we get this anomaly. We get this sort of artifact that the thing we're trying to use, ionization energy, we're really just trying to use it for the idea of trying to get a sense of how attraction of those electrons changes from left to right with the nucleus. But we just have a varying type of orbital that's losing the electron from left to right. We're losing the electron from an s orbital over here, and then from p orbitals over here. And then what about this group here? What about the oxygen group? Why are they not higher or as high as you would expect compared to their neighbors in the nitrogen group of elements? So why is oxygen a little bit lower than nitrogen? Well, this all has to do with spin pairing. That when we spin pair electrons, that causes there to be a repulsion. And so we kind of destabilize that orbital in oxygen. So removing electrons a little bit easier than it should have been than maybe we would have thought just looking at nitrogen. So we have this electron repulsion issue for the NP4s. And so there is a nomenclature in one of the homework problems that, we could call this group here, the boron group, the NP1, meaning they're putting their last electron into a p subshell. So NP1 would just mean for boron, it's like a 2p1 configuration. For aluminum would be a 3p1. If you look at the oxygen group, I know this is getting pretty sloppy here, but the oxygen group would be an NP4, so an NS2 NP4. So 2 electrons in an s orbital, 4 in the p. The boron group was an NS2 NP1. So sometimes you see this lingo just for the N just being, if we're talking about boron, it's a 2s2, 2p4, or excuse me, we're talking about oxygen, it's a 2s2, 2p4. If you're talking about sulfur, it's a 3s2, 3p4. Selenium would be 4s2, 4p4 outer configuration. So these configurations here are just a little bit easier to lose electrons from due to some what I would call configuration anomalies. So ionization energy generally increasing, but with that periodic inconsistency from left to right. And then if we just inspect, let me do a little erasing here from this side here, just to see the general decrease. And also notice hydrogen's really high ionization energy compared to the other, compared to the metals in the alkali group. So hydrogen, because of this relatively high or a lot higher ionization energy, doesn't fit into the same trend as lithium, sodium, potassium, rubidium. This is a big reason why hydrogen's not a metal. Hydrogen wants to keep that electron more than the other alkalis do, where they can kind of have that electron almost be borrowed by all the atoms within a block of sodium metal, lithium metal. Hydrogen wants to share its electron with one other atom, and that's it. you can have a chunk of sodium like we were putting into water where all those atoms are kind of sharing that outer valence electron with each other. So much different set of properties for hydrogen compared to the other members in that group of elements. But notice that you have this big decrease from hydrogen to lithium, then a relatively small decrease in ionization energy from there. And so we get a decrease in ionization energy. Why might that be? Well, if we inspect this equation, we actually have two counter-opposing trends. So this equation here would say as you go from lithium to sodium to potassium, that outer valence electron is moving further away. If you put that electron further away, then you're going to weaken that electrostatic attractive force. So just imagine you have a positive particle here. If you have a negative particle very close, that's a strong attraction. If you put that negative particle 2 miles away, not much of an attraction for those ions that are farly separated. You can think of this in terms of attraction of, as you get closer together, more attractive than if you're far away. So you got to be close together to sense that attraction. Same thing with plus and minus charges here. So the further away the charges are, the weaker that attraction is, the easier it is to overcome. But now we do have also the effective charge, though, slightly increases. If you recall, the effective nuclear charge is actually increasing, but not by much as you go from top to bottom. The increase in effective charge might have made you think ionization energy should increase from top to bottom. So we have two counteropposing trends. Effective nuclear charge is going up, but the size is going up. The size is what generally wins out. So from top to bottom, we get this general decrease in ionization energy despite the increase in effective charge, and this is due to the increase in size of the atoms changing by a greater quantity as you go from top to bottom. Now, some of the groups of elements, you can see a few, like the zinc, the cadmium drops, but then you increase here. If you notice, the third row transition metals are all higher than the second row transition metals in ionization energy. You see a few trends, like lead is a little bit higher than tin. So you can see a few elements are higher than their element directly above them on the periodic table, and you can explain that in terms of, for those atoms, it must be that their size didn't increase by as much as their effective charge increased. So you can even then explain why some elements don't follow the general trend of a general decrease. So if we give you an element at the top of the table versus an element at the bottom, you can know for sure that the ionization energy is going to decrease. And for most of the elements, even that are directly above each other and below each other, that as you go down, you get the decrease in ionization energy. And only in a few cases do you get that increase in ionization energy. But at least when you do, you can understand and put a explanation to the trend that in those elements, that's where the effective charge trend was beating the size trend. So ionization energy. Generally, you get the increase left to right because atoms are becoming smaller left to right. As size decreases, that's because the effective charge is increasing from left to right. You have the increase in charge and a decrease in size. Both of those point towards the ionization energy increasing. Just configuration anomalies, they'll lead the MP1, MP4 to be a little bit lower, and then the decrease from top to bottom.
So does that coincide with how the decrease in the 2s and 2p and the 3p and the 3s, does that drop coincide with do you get what I'm saying?
So this drop here.
Yeah. So why is it larger than all of the other drops?
So why is the beryllium to magnesium a bigger drop than some of the other groups, or why is the N equals 2 to 3? I mean, probably the best explanation would be that it's the same issue with the Bohr model. 1 to 2 is a big difference of energy. So the N equals 1 to the N equals 2 difference in size is a big change in size. So a huge drop off from hydrogen and helium to their elements down. And the same thing, the second to third row, big change in size. I think as you start going up in the Bohr model, you know how the energies start getting closer together, then the size difference starts to get smaller. So I think as you go from the third row to the fourth row, the size isn't increasing by as much. It's probably why you see them becoming a smaller difference, but still a general decrease. Okay, now this question here, I didn't throw this into the notes, so if you want to kind of jot this down and we'll think about this here. We wanted to compare the effective nuclear charges, but for all the electrons in sodium, chlorine, potassium, and then also for zinc. Now, when I say effective nuclear charge, we symbolize it this way. If I just said, what's the effective nuclear charge of sodium versus chlorine, you'd always be thinking the valence electrons. Like if I don't say, consider the effective charge for some other subshell, you're just assuming that I mean for the outer valence electrons. But I could say for any of these elements, I could say, well, for like a 1s2, for sodium, 1s2, 2s2, 2p6, 3s1 configuration, that the effective charges for these subshells just kind of goes in the order of those subshells. So the 1s experiences the highest effective charge, then the 2s the next lowest because it's screened a little bit by the 1s. The 2s screens the 2p a little bit, not by much, but by a tiny fraction, and then those are all screening the 3s electrons, so the outer valence electrons experience overall the lowest overall effective charge. And so this is just what we are kind of seeing with the lowest charge being experienced by the valence electrons. And then for chlorine, same thing. So we're just thinking for chlorine, it's a 1s2, 2s2, 2p6, 3s2, and it's 5 across the 3p. And so we just have the 1s experiences the greatest charge, then the 2s, then the 2p, then the 3s, then the 3p. So like the 3p subshell would experience for chlorine its lowest overall effective charge of any of its electrons. And then you could compare and say, well, for sodium versus chlorine, which one of these subshells, like we could ask a question like, which of these subshells between sodium and chlorine experiences overall the highest effective charge? If I said which of the subshells, like the 1s of sodium versus the 1s of chlorine, which one of those subshells experiences the overall greatest charge? And it's beyond a doubt would be the chlorine. So like this one here experiences overall the highest charge of these subshells for these two atoms, just because it has the highest overall Z. The effective charge, or the total charge of chlorine is 17 plus, chlorine's 11 plus, so the 1s of chlorine's experiencing about that full charge of 17 plus. Sodium only about 11 plus. Then if I said which of these subshells experiences overall the lowest effective charge, so just considering all these different charges here, the lowest overall would be the 3s. Now, why is that the lowest overall? Well, we just go back to the idea that effective charge is increasing from left to right, so the 3p of chlorine is going to experience a lot higher of an effective charge than sodium. So this is why sodium has a big size, and chlorine, despite having more electrons, is overall smaller. So the size is decreasing from left to right, so chlorine's smaller than sodium. Okay, now let's look at potassium for a minute and compare it to zinc. So if we look at potassium, we have a 1s2, 2s2, 2p6, 3s2, 3p6, followed by a 4s1. And so if we wanted to rank order all these subshells, of course, it'd just be the 1s is experiencing the greatest, then the 2s, then the 2p, then the 3s, then the 3p, followed by the 4s. So of course, the 4s is experiencing for sodium its lowest effective charge. Its 1s is experiencing overall the highest effective charge, and the others in the middle. Now, what happens though for elements like zinc? In fact, I don't know if we've really thought about this too much in terms of where the 3D subshell electrons are compared to the 4s. But let's think of its configuration first, and then let's think about where these electrons are. So, I mean, let's do the full configuration because it's easy enough to write. Let me also restart here real quick. Make this a little bit bigger so the font size is consistent. So we have zinc. So we'll have a 1s2, 2s2, 2p6, 3s2, 3p6, then the 4s2, and zinc's all the way across the D shell, so it's a 3d10. Now, quick question for zinc. How many valence electrons does it have? Those are the only two valence electrons. According to our rules, outermost shell, so these are the two valence electrons. Remember how I said earlier the valence electrons should experience the overall lowest effective charge? So the effective charge for zinc is actually going to go in this order. So it's going to go 1s still is greater than the 2s, greater than the 2p, greater charge than the 3s, greater than the 3p. So very consistent for like sodium and chlorine that we'd already seen. Same thing for potassium, so nothing different. But then the 3D comes next, then the 4s. Like, how did I end up with this switch here? Where we were thinking of the electrons kind of first going into the 4s, then into the 3D, but how is it that the 4s ends up with the overall lower effective charge? Well, one way is that these are the valence electrons, meaning they're the outermost. And being outermost is probably really important for ionization, because if you're thinking the outermost electrons are further from the nucleus, so that's going to mean that they're held on to weaker by that nucleus. And so what goes on for this configuration, if you think of where all these electrons are for zinc, so think about zinc 30 plus nuclear charge total. So you have a 1s, a 2s, a 2p set of orbitals, and those are all absorbing some of the positive charge, making that positive charge not make its way out to the outer valence electrons. Then we have the 3s subshell, followed by a 3p set of orbitals. Then we have the 4s. Then where are the 3d? The 3d are smaller, so the 3d, let me change color for the d orbitals. D orbital would be right here. So notice that the d orbital is in that like n equals 3 space. So you have the 3s, the 3p, then the 3d is in that same general vicinity of space. It's using the space in between the p orbitals to maximize where it's putting its electrons. And so notice that that space is closer to the nucleus, so therefore it must be experiencing both a greater charge because it's closer to the nucleus on average, and then also because it's closer to the nucleus experiencing a greater charge, think about the kappa Q1, Q2, divide by D problem. So we have those electrons experiencing a higher charge and they're closer together, closer to the nucleus. So the ionization energy of those 3D electrons is going to be higher than the 4s. The 4s is further away, experiences overall the lower effective charge further away, reducing that ionization energy. So the most easily ionized electron from zinc is going to be the 4s. And also, it's valence electrons. The valence electrons should be the ones that are most important for understanding the bonding in something like zinc. So it shouldn't be too surprising that the configuration, say, of zinc 2+, when we take 2 electrons off of zinc, that the configuration is going to be an argon configuration followed by a 3d10. That we're going to lose the 4s electrons first. And this isn't some like anomaly. This isn't some weird rule for zinc that the other elements don't do. All of the transition metals are going to lose electrons first from the 4s subshell.
So, like, how do you pick like what element is going to be like when you do that? Like highlighted, like why is it argon?
Oh, this one here?
Yeah.
I mean, we could have written I could have written 1s2, 2s2, 2p6, 3s2, 3p6,
So, but like
3d10, but the key being, I could have written all of this that I wrote before, and then, you know what I mean? But the key is that we can just save time and say that all of this here is just argon. And argon's a noble gas, so like we do it commonly with a noble gas that then precedes the row that we're in. So going like an argon, so like zinc, for example, we could write zinc with the full charge was an argon 4s2, 3d10. And so the issue is when you're taking 2 electrons away to make the ion, that we take those electrons away. Even though they weren't supposedly the way we were thinking about configurations, the first electrons assigned. We were putting electrons by energy into the 4s, then to the 3d, but then we take them out of the 4s first. And we take them out of the 4s because 4s is further from the nucleus and therefore experiences overall a lower effective charge. So this question here, this is more or less kind of like what this question was getting at, where it says electrons in which subshell of a ground state zinc atom. Like whenever we're doing configurations, whenever I say give me the configuration of an atom, we mean the ground state, the lowest energy state of the molecule, the most stable state. So the most stable state of zinc would be that argon configuration followed by a 4s2, 3d10. And these are further from the nucleus. These are closer to the nucleus. They experience the higher effective charge, harder to remove. In fact, they're so hard to remove, zinc never actually removes them. Zinc 2+ is the only common ion of zinc. That's how strong those 3d electrons are attracted to its nucleus. So the zinc 2 plus configuration should be a 3d10. We lose those 2 electrons. And then a lot of times we ask the question of how many unpaired electrons a configuration has, just to make sure that we're picturing having 5 d orbitals. And then we got to put 10 electrons into them, so 5, 6, 7, 8, 9, 10. So the electrons in the 4s subshell experience the lowest effective charge, and then we have 0 unpaired electrons in the configuration. So asking the unpaired electron count is a way that we can try to make sure that you have the right configuration. So questions like this sometimes will ask, well, what is the configuration? We could also ask how many unpaired electrons you have. The key is seeing that zinc 2 plus is not going to be an argon 4s2 3d8. That's not the configuration. Like, you don't lose the 2 electrons out of the D, you lose them out of the S subshell. And that's just our rule for cation configurations. You lose the electrons first from the outermost electrons. So you lose the outermost electrons first. Those are the ones with the highest N value. And if you have more than one N value, the N value with the highest L value. So these electrons are lost first in ionization. So you lose the electrons in a configuration from the highest N value orbital. If you have 2 orbitals that share an N value that are the highest, then the highest L value. And we'll do an example that kind of compares the L value in a moment. Okay, so cations. So electrons are first lost from the largest orbitals, the highest N value with the greatest L. So if we're looking at calcium 2+, what this kind of means, if you're trying to determine a cation's configuration, think first of the neutral atom. So think first of calcium neutral. So calcium neutral would be an argon 4s2. And so you really have no choice here, right? Like, obviously we're going to lose the 4s electrons because these are the highest N with the highest L. So that would be the 4s. So we lose the 4s electrons first. So calcium 0 or calcium 2+'s configuration will just be that of argon. So you can say that the calcium 2+ configuration is just the argon configuration. So you lose 2 electrons, you come up with a count of 18 electrons matching the same configuration that argon has. Iron 2+ is element 26. So think of iron neutral. So iron with no charge would be an argon 4s2, 3d6. And so iron 2+, we lose the 4s first. So highest N with the highest L. You don't lose the highest L overall, the highest N value subshell with the highest L value. So that's going to be this one here. So iron 2+ should be an argon 3d6. So what if you need to lose one more electron from iron and make the iron 3+ cation? Well, if we got to lose one more electron, highest N with the highest L. So N equals 3, L equals 2 is now the next largest subshell. So iron 3+ will be an argon 3d5. Because we have no other choice then to take electrons from that D subshell. Now, anions are really pretty easy. Anions, you'll just continue along with the process that you would kind of think. Like, so oxygen neutral. So oxygen with a neutral charge is a 1s2, 2s2, 2p4. So you just put 2 more electrons in to that subshell that we're filling here. So this just becomes a 1s2, 2s2, 2p6. So we just cap off that N equals 2 subshell. This is the same configuration of neon too. So you can say that this is just the neon configuration. N3- the same thing. So we have a 2s2, 2p3, add 3, also to the neon configuration. And so argon minus, what if we add an electron to argon? It's going to be pretty hard to do this, but this would be the argon configuration, so we could just base it on its own configuration, then plus the 3s1. So configuration of argon with a minus charge is just the same configuration argon had, followed by not 3s1, but the 4s1. So argon is in the third row, so the next electron would be a 4s1, actually. So it should be a 4s1. So let's do a couple that kind of get into some bigger elements. So bismuth is all the way element 83. It's in the nitrogen group. So bismuth, element number 83. Bismuth 3 plus, well, let's just think of bismuth neutral first. So even though bismuth is pretty big, hopefully we can come up with this configuration. So the configuration of bismuth would be xenon, go to the nearest noble gas that precedes it. So that's xenon. And then xenon has to go across the 6s2. So that's calcium and barium. We got to go across the entire lanthanide series of 14 elements, so that's a 4f14. We got to go across the whole next D subshell. So scandium's group is a 3D, yttrium's group is a 4D. So the third D block is a 5D, so that's 5D10. And then followed back to the 6p3. So now, again, how do you know bismuth is a 6p and not some other number? How do you know this is a 6? We'll just go boron's row, so nitrogen's a 2, phosphorus is a 3p, arsenic's a 4p, antimony's a 5b, so bismuth is a 6p. So you're just counting downward. So we got a 6p3 here, and so then the highest N value is 6. So that's our outermost shell. So these are our valence electrons. If we were doing the valence count, we'd say 5. Remember, if nitrogen has 5 valence electrons, every element in that row has 5. So 5 valence electrons. And so highest N with the highest L is the 6p. So my bismuth 3 plus electrons, I'm going to lose the 6p3 electrons first. So bismuth 3 plus should be a xenon configuration, followed by 6s2, 4f14, 5d10. Lead 2 plus is right next to bismuth, same basic thing. In fact, this is kind of boring, but lead 2 plus based off lead 0, so xenon, 6s2, 4f14, 5d10, and then just say 6p2. And so lead 2 plus, of course, is going to lose the p electrons first, so this would be a xenon configuration, 6s2, 4f14, 5d10 configuration. And then what about if we need to lose 2 more electrons to go lead 4 plus? Where do you think they come from? Probably the other 2 valence electrons. So we're going to lose the 6s next. So we go xenon, 4f14, 5d10. And so this is just kind of showing you that the valence electrons are the important ones that are going to be the outermost. They're going to be the ones that are lost first to make cations. So the last topic in chapter 7 is electron affinities. And electron affinities, the energy associated with absorbing an electron. So all of the energies on this chart here are the energies associated, let's do chlorine. So this is the energy associated with chlorine as a gas absorbing an electron to form chlorine minus as a gaseous ion. And so this energy here is what corresponds to the electron affinity of chlorine. So if you notice, most of the electron affinities in this table are negative. Chlorine's is minus 349. So the electron affinity is kind of like the delta H or the delta E of this equation, that the chlorine atom is becoming more stable by absorbing an electron. Okay, so absorbing an electron is favorable. So we take an electron off of sodium, takes energy. It takes about 500 kilojoules per mole to take an electron off of sodium. If we put that electron onto chlorine, we get 350 kJs back. So now, why does sodium chloride as a solid form? We'll see this in chapter 8, but sodium chloride as a solid is going to form because once those ions form, they have an attraction. Now, how do electron affinities compare from left to right? One thing you can see is that we have a really negative group in the case of the halogens. So our halogen group's the most negative, and so electron affinities are becoming most negative towards the halogen. If you notice, they're the most positive for the noble gas group. So you can imagine the noble gas kind of resets the electron affinity trend because the noble gases have nowhere else to put another electron. The halogens benefit for electron affinity for a couple reasons. They're the smallest element. They also have room for an electron, and they have that high effective charge. And so they have the charge to pull an electron in, and they have room for the electron in their valence shell. The noble gases are the worst because despite being small, they have nowhere else to put an electron. So they have to put an electron into a much bigger subshell that's a higher energy subshell, and that's unfavorable. So the noble gases are the most unfavorable group. So the most positive electron affinity is bad for electron affinity because it means it takes energy for the elements to absorb an electron. And then the other groups, though, are mostly negative, but with the exception of the NS2 group and the MP3 group. For the MP3 group, you can realize is high because you have to spin parent electron. And then the NS2 group is high. I'm sure they're coming to it over here. That is because you have to put the electron into a larger subshell. You have to put the electron into an MP1 to a bigger orbital, which is further from the nucleus. So we kind of have the same anomalies in the NS2 group, in the MP3 group, just like our electron affinities had the anomaly here. So it's the same basic reason for the anomaly. So we're becoming more negative towards the halogens and then resetting ourselves with the noble gas group. Not much of a top to bottom trend. So if you look at the elements from top to bottom, we kind of have a decrease and then followed by a slight increase. So the third row happens to be the most negative. I don't think I would memorize that detail, but the third row elements are most negative in electron affinity, probably because the balance of size versus charge. So fluorine, small, but not the highest effective charge. Effective charge is increasing from top to bottom. So chlorine has a higher charge, but it's bigger. And so remember before we were kind of discussing with ionization energy that as charge goes up but the size goes bigger, that the size trend won out. Here we're seeing kind of the size in the third row is best. So for whatever reason, the size in the third row for electron affinity allows them to have the most negative ability to accept an electron. Not a very big detail, but there's not much of a top to bottom trend other than the third row elements are the most negative, presumably because they have the best balance of size versus charge. Okay, a couple of chapter 7 review problems here before we get into some other review topics. So which atom in each pair has the greater effective nuclear charge? So take a minute or two to think about this one. You can talk with your neighbors if you wish. All right, so what do we think here? What do you guys think?
I think it could be fluorine, but I'm not sure about the other one.
So effective charge increases from top to bottom. So that's one thing we have to remember is effective charge is going to be the highest at the bottom of a group. So iodine is going to be higher, and then it increases from left to right. So effective nuclear charge increases from top to bottom and left to right. So from left to right, we have a decrease in size. Increase in charge coincides, or the decrease in size is because of the increase in charge. And from top to bottom, we do have an increase in size. Fluorine, chlorine, bromine, iodine. Iodine is becoming bigger, but because they have more electrons. So the top to bottom trend is because we're using larger types of orbitals to make the configurations. But the effective charge increases because if you imagine having, like, do you remember these curves? So if you imagine having, say, a 6s subshell, remember how it would have kind of that type of thing where we'd have 5 nodes for a 6s. So we'd have 1, 2, 3, 4, 5 nodes for this orbital. All of these little probabilities, the electron being relatively close to the nucleus, add up to the 6s, like an orbital in the 6s having a relatively higher effective charge because of all those probabilities. That's also the core electrons in this region here are just not absorbing as much charge either. So as you go from top to bottom, you get a slight increase in your effective charge. So iodine is going to be higher than fluorine, and then chlorine will be higher than sodium, so that should be answer D. Another question is thinking about charge of atoms versus ions. And so when we're comparing charges here of uncharged atoms, we use the atomic radii trends. And those are the trends that size decreases left to right. But then increases top to bottom. But then here we need to use the isoelectronic series comparison. We got to compare the number of protons for the case where we have for K plus and Cl minus. The issue here is K plus loses an electron, has 18 electrons. Potassium has 19, losing electron has 18. Chlorine has 17 electrons, so if it absorbs one, it also has 18 electrons. So isoelectronic just means they have the same electronic configuration, and so they each have the configuration of argon. And so the configuration that has more protons to pull those electrons in goes smaller. So K plus is smaller than chloride because they have the same exact electron configuration. They each have 18 electrons. If you had a greater positive charge, couldn't you pull those electrons in more closely? So if you're picturing that configuration, if you're picturing like a 1s2, 2s2, 2p set of orbitals, 3s2, 3p set of orbitals, and you're picturing all these orbitals, if you had a 19 plus versus 17 plus, isn't that 19 plus going to pull those electrons in more closely? And it does. So K plus is smaller than chloride. So we just got to be careful when comparing potassium and chlorine. In the case of ions, if they have the same number of electrons, we're using the isoelectronic series. And then if we're trying to compare the size of potassium versus chlorine, we just use our left to right trends and our top to bottom trends. And so potassium on the far left, chlorine on the far right. What I'm going to do to make this comparison is compare both of them against sodium, because I know potassium is bigger than sodium. I know sodium is bigger than chlorine. Therefore, I know K must be bigger than chlorine when they don't have a charge. And so chlorine is smaller than potassium when we're comparing chlorine with 17 electrons, potassium with 19 electrons using our trends of atomic size. But then we just have to remember that K plus is smaller than K. Chlorine minus is bigger than chlorine. I wrote this backwards. K plus is smaller than potassium. Take an electron off of potassium, K plus is smaller. Add an electron to chlorine, it grows bigger, such that we reverse the trend. So we had this trend here where potassium is bigger, but then K plus becomes smaller than chloride. So we get a swap. But it's just a simple swap we can understand by comparing protons when they're isoelectronic, and then comparing left to right trends when they have their ordinary charges. All right, so let's look at a chapter 5 review. So chapter 5 just has one section on the test. It's the bond enthalpy section. So it's using bond enthalpies to predict delta H's of reaction, and also just to generally understand that when you break a bond, breaking any bond, if you notice the entire chart has positive bond enthalpies. So breaking bonds is always endothermic. The bond has to absorb energy to break because there's some stability holding that bond together. So if we think of electrostatic potential energy, I know there was a word and a phrase from the last midterm. Like if you have a plus and a minus ion, you bring them together, the energy drops. If you have two positive particles, bring them together, the potential increases, the electrostatic potential increases. If you have a bond like H2, so H2 is down here, to break the bond into two H's, you have to have energy absorbed, 436 kJs per mole for that bond. So 1 mole of H2 has to absorb 436 kJs per mole of energy in order to break. And so all bonds, to break them, are endothermic. And if you form a bond, if you do the flip of the reaction, so two hydrogen atoms forming H2, of course this is going to be exothermic. So making bonds is exothermic. And so then we can approximate delta H. So who remembers what's interesting about approximating delta H here? One is that you get an approximation, not necessarily a direct equality, because these are average bond strengths, not necessarily exact bond strengths. But then we get a prediction from the sum of what? The bond strengths, but of the reactants. So we got to take the sum of the reactants bond strengths minus the sum of those of the products. And so we're trying to address the issue, how much heat does it take to break all the bonds in the reactants, and then how much heat do we get back when we make all the bonds in the products? So we break all the bonds in the reactants. How many bonds do I break in the reactants? I break the NCl bond 6 times. So I have 2 NCl3s. Each NCl3 has 3 NCl bonds. We'll show you a structure. You don't necessarily know how to sketch Lewis structures for every compound, so we'll show you a Lewis structure for this topic. And so we have to break 6 moles of the NCl bond. The NCl bond is 200 kJs per mole. Then I have to get back the energy when I make my new bond. So I then subtract the bond energy for nitrogen-nitrogen triple. So that's 1 bond times 941 kJs per mole. Then I have to add the second bond that's being made, the chlorine bond. I'm making 3 of those, and that bond strength is 242. So let's do that math. So 6 times 200, and then minus the sum of 941 and 3 times 242. So that ends up being minus 467 kJs per mole. So the key is, remember, it's reactants minus products, but it's the sum of the bonds we have to break in the reactants minus the sum of the bonds we form in the products. There are harder and easier versions of this problem. Sometimes you might have a reaction where only some of the bonds are broken in the reactants and you make some new bonds in the products, but you could always just break all the bonds in the reactants, every single bond there is, and then make every single bond there is in the products. All right, so let's compare to a 725 nanometer photon. Which statement is true about a 625 nanometer photon? Okay, so as we look at the light travels at the speed of light, and it's equal to the frequency times the wavelength, so lambda times the frequency. And so as the light moves to a lower wavelength, it has to move to a greater frequency because light has to travel at the same speed of light. So the radiation doesn't change its speed of light because it changes wavelength. The speed of light is the same for both photons. So statement 2 is incorrect. And to move to a lower wavelength would mean we go to a greater frequency. So statement 1 would be true. So you could also just calculate the 2 frequencies and compare if you want to and just use the speed of light. Let's move on to a question like number 6. So the ionization energy of sodium is 496 kJs per mole. I don't know if I ever mentioned this name, but Hertz did the experiment that actually discovered that if you shine light on metal, it can eject electrons. And we were talking about this, that the light just had to be of great enough frequency. It had to be of great enough energy that we now know had to be great enough energy. And it had to be of a certain wavelength or lower. So the light had to be of a certain frequency or greater, a certain wavelength or lower. And then this is what then allowed Einstein to determine that the energy was being carried by the photon. So this is what led to the discovery of E is equal to h nu equal to hc over lambda. So this experiment done by Hertz, he passed away, I don't think I ever mentioned this, but he died, I think, in his 30s before he could actually try to explain why the phenomenon was being observed that he was seeing in his experiments. But this photoelectric effect is just the idea that you couldn't take light that had the wrong frequency and just use more photons. So if you had light that just had too low of energy, if you had a light that was just of a wavelength that was too high, so the wavelength's too high, it doesn't carry enough energy. If you just shine a brighter light source, it doesn't do anything. It doesn't cause the electron to be ejected by the metal. But what we saw is that you just have to go to some threshold energy. The way we calculate the actual wavelength associated with the ionization is to think about this per atom. So you think per sodium atom. We have 496 kJs per mole. Let's just take that value, 496 kJs per mole, and let's use Avogadro's number. So 1 mole of sodium is 6.022 times 10 to the 23 sodium atoms. So just using Avogadro's number. So I'm going to do 496 kJs per mole, divide by 6.022 times 10 to the 23. That gives me 8.24 times 10 to the minus 22 kilojoules. Let me multiply that by 1,000 joules. I'm going to multiply the joules here because I'm going to use Planck's constant, which has units joules times second. So when I go to calculate the energy that I need the photon to carry, and I want to calculate the wavelength associated with that energy, I want to use Planck's constant units of joules times seconds. So I just multiply by 1,000 here. That gives me 8.24 times 10 to the minus 19 joules. It's 19. Okay, so 8.24 times 10 to the minus 19 joules is the energy I need my photon to contain or greater. So I need the energy of my photon, which is hc divided by lambda, to be greater than or equal to 8.24 times 10 to the minus 19 joules. And so this allows you to calculate the wavelength, but if you cross multiply wavelength, wavelength needs to be less than or equal to hc divided by that energy. And so h, this is given on the test if you forget it, but h is just 6.626 times 10 to the minus 34 joules times second, so that's why we want to go joules here. Write your units out. Sometimes I see students missing or not including their units in their work. If we forget units, we may not realize kJs need to go to joules, and if you're showing your units, it's really pretty obvious that we had to convert into joules. So we go 6.626 times 10 to the minus 34, and then times the speed of light, so times 2.998 times 10 to the 8, which I think we all know the speed of light, but again, just multiply by the speed of light, meters per second. So the meters per second cancel here, and then we get our wavelength out in units of meters. So we get that our wavelength has to be less than or equal to 2.41 times 10 to the minus 7 meters. And if you convert that to nanometers, 1 meter is 10 to the 9, so multiply by 1 E9, or by 10 to the 9, you get 241 nanometers. So not only do we calculate the number, but by thinking of the sign, by saying we need the energy of that photon to be greater than or equal to 8.24. The photon has to contain at least that much energy or higher, requires it be at 241 nanometers or lower in terms of wavelength. So going lower in wavelength is higher energy. So going to a lower wavelength, greater energy, so we need to be at 241 nanometers or below. So these questions here, and almost like any question that gets at a phenomenon that relates to light interacting with matter, you need to be at some threshold wavelength or lower in wavelength. If we wanted to calculate the frequency, it's just that we tend not to characterize light by its frequency. So these problems here usually don't say to calculate the frequency of light because, if you said this light had 10 to the 14 inverse seconds of frequency, that doesn't tell me anything, or at least I wouldn't know immediately what region of the electromagnetic spectrum that's in. I know this is a UV photon. So how do I know this is a UV photon? Question I've gotten, this was in the email, but 400 to 750 nanometers is what I really want everybody to know, that this is blue-violet light and that this is the red part of the spectrum. So below red in energy is infrared. So infra means below. So below red in terms of energy is infrared. So the IR is on this side here, and then UV's on this side here. X-rays even higher. Gamma rays on the higher energy side. So just know the general orders: gamma rays, X-rays, high energy, then UV, then visible, then IR, microwave, radio frequency. I don't think knowing the specific cuts is all that important. I'm not going to give you a photon that's like, never going to give you like a 25 nanometer photon and ask you what region of the electromagnetic spectrum it's in. Or if I did, you should be able to identify that it's either maybe microwave or radio frequency, but not between those two. Like you could probably guess that it's not visible or not UV. You might be able by process of elimination to figure out that it's not gamma ray, definitely not, or I'm sorry, 25 nanometers is smaller side. So that would be on the UV side. So you can generally figure out if it's not in a certain region. Like if we give you a photon that's beyond 750, then I could expect you to know it's IR, microwave, or radio frequency, but maybe not specifically which one of those three regions, if that makes sense. So just nailing this region here, and then the order of the other regions is really what's most important. So which transition of the H atom would emit a photon with the longest wavelength? So the next question down, the longest wavelength photon. So emission occurs when we have a high energy state transition to a low energy state. So when we go from, let's see the choices here, 1 to 2, from 4 to 3, so 2 to 3 to 4, so 4 to 3, 4 to 5, 4 to 1. So for these, to go from a low to a high, this requires the absorption of energy. So choice A would require energy to be absorbed, not emitted by that process. So that can't be a possible answer. Also, C requires the absorption of energy, not emission. Now, B and D would lead a photon to be emitted. So when you go from a high energy state to a low energy state, light can be emitted. And so the difference of energy from the 4 to 3 is a lot smaller. So the delta E here is smaller for the atom. So the energy of the photon it gives off is going to be a lower energy photon. A lower energy photon compared to the 4 to 1 transition being a big delta E. This will give off a photon of a lower wavelength. This will give off a photon of a higher wavelength. Higher wavelength, lower energy. So the energy that the atom loses goes into creating a photon. This is kind of like the photoelectric effect. One atom loses energy, creates one photon. The photon energy is just equal to the energy difference that the atom undergoes. Small energy difference, long wavelength, big energy difference, you're talking a big energy. So this is likely going to be a UV photon for the 4 to 1. The 4 to 3, this is probably in the IR range, a low energy region of the spectrum, a longer wavelength region of the spectrum. So answer here should be the 4 to 3 has a longer wavelength. You can calculate that energy. So if you said, well, what is the wavelength for the 4 to 3 transition? You have two basic ways of doing this problem here. If you said, what is the wavelength emitted by the electron going from n equals 4 to n equals 3 in the H atom? Well, the two approaches you have are to use this equation here. And this is given on the test. If you look on the sample info packet, this is a given equation. Rydberg constant is given on the packet too. This is probably the easiest way to go. You just plug in the 4 here, plug in the 3 here, plug in the 4 here. The only hard part of this equation is just knowing which end goes where, but if you get this backwards, you would just get like a negative wavelength, and you would know that you just had the ends backwards. So here the N1 is just so N1 is the smaller of the N values. But now the other approach that we could take is to calculate the delta E of the H atom by taking the energy of the final state to the 3 minus the energy of the 4 state And then just plugging in negative 2.18 times 10 to the minus 18, 1 over 3 squared, minus negative 2.18 times 10 to the minus 18 joules times 1 over 4 squared, getting that energy difference here in terms of the number of joules, and just setting that equal to hc over lambda and solving for our wavelength. It's more steps, but the second way, if you do it at least once the second way, and if you've done it already, you can understand that you're just calculating the energy lost by the atom that goes into creating the photon. So to me, it makes a little bit more sense because you're seeing the energy, the atom loses energy, the energy goes into the photon's energy and creates the photon, and you can calculate the wavelength. So two approaches. This one's probably easier because the wavelength falls out. You don't need to do a couple steps. But that's how we can look at a problem like this. The answer is like 1876 nanometers, I believe, if you want to check your work. A key's posted for all remaining problems, but I'll get to the remaining problems Monday in lecture, or check the key if you want to check some work over the weekend. A bunch of practice exam packets are available. Check those out. Good luck preparing for the exam, and I'll see you guys on Monday.